Okay, hello guys. So I'm back with my voice now. So if you guys watched the part 1, that was a disaster. So let's continue. So this is the second part of the race condition because I needed to take a break because it was very frustrating and I need to get back home and I'm home now. So I'll continue. Yeah. Okay, so we'll go back to our old rules. So I will not show you guys my notes again, but at least in this session, but I will try to explain what I understand from the path. Yeah, that's it. So let's continue. So this time they are talking about single endpoint race conditions. Let's read. Sending parallel requests with different values to a single endpoint can sometimes trigger a powerful race condition. Consider a password reset mechanism that stores the user ID and reset tokens in the user sessions. Ooh, okay. User ID. This is very interesting actually. In this scenario, sending two parallel password reset requests from the same session but with two different usernames could potentially cause the following collision. Yeah, so when he requested the reset user for the account hacker, he also requested for the second account called victim. Ooh. Note that note the final state when all operations are complete. Victim reset token 1234. Okay, so that's a bit weird because the reset token is set to oh, because after he set the reset user, it will replace the reset user with the victim. Then it will replace the reset token and to 1234 and to hacker. So it's valid. Wait, let me save that to my notes. That's actually pretty cool. Yeah, this one is very interesting. I feel like this one is very cool. Okay, so let us continue. Let me make the song bigger. So single endpoint race conditions continued. The session now contains the user victim's ID, the victim's user ID, but the valid reset token is sent to the attacker. Note, for this attack to work, the different operations performed by its process must occur in just the right order. It will likely require multiple attempts or a bit of luck to achieve the desired outcome. Email address confirmations or email-based operations are generally a good target for single endpoint race conditions. Emails are often sent in a background thread after the server issues a HTTP request to the client, making race conditions more likely. Interesting. So let's save this part. Yeah, nice. Okay, and continuing. This Labs email change feature contains a race condition that enables you to associate an arbitrary email address with your account. Someone with the address Carlos has a pending invite to be the administrator for that site, but they have not yet created an account. Therefore, any user who successfully claims this address will automatically inherit admin privileges. To solve the lab, identify a race condition that lets you claim an arbitrary email address. Change your email address to K. Okay, this actually sounds a bit hard. Hopefully, it's not that hard. Okay, task. Yeah, task. Okay, let's try. Email client. Where's the... There's actually no email. Wait, what about the... Wait, let me try to find... Oh, here it is. Let us put it on our notes so we can remember. Okay, so let's try updating our email. So let's send it. Okay, so this is a bit interesting. What if we try to make a group? Then we can try to duplicate this, but the second one uses this email. What happens? So let's check. Did it? Yeah. What if we send it in a parallel? Nope. This link is invalid. Well, that's a bit sad. Mm, Okay, so I think I need to read the solution because I'm a bit confused. Okay, I'll just see the video because I don't understand what's wrong. But doesn't work on my what? So it requires a bit of luck. Oh, do they did it? Let's try. Nope, it didn't work. I'm so confused. Why can't mine work? What am I doing wrong? Doesn't work. Huh? Why is the link invalid? I don't even understand why. Why is it always invalid? I don't understand why. I'm a bit confused. Even the newer links are invalid. I don't understand anymore. Okay, this type is just stupid, man. He won't let me finish. I don't even understand why, though. Like, I did everything that she did or he did, but it doesn't work on my lap for some reason. It's so confusing, man. Why doesn't it work? Okay, the challenge is broken, man. I'll just skip it. It's very frustrating. Okay, let us just continue and skip that annoying lap. Okay, so we are going in session-based locking mechanisms. Some frameworks attempt to prevent accidental data corruption by using some form of request locking. For example, PHP's native session handler module only processes one request per session at a time. It's extremely important to spot this kind of behavior, as it can otherwise mask trivially exploitable vulnerabilities. If you notice that all of your requests are being processed sequentially, try sending each of them using a different session token. Okay. Partial construction race condition. Many applications create object in multiple steps, which may introduce a temporary middle state in which the object is exploitable. For example, when registering a new user, an application may create the user in the database and set their API key using two separate SQL statements. This leaves a tiny window in which the user exists but the API key is uninitialized. This kind of behavior paves the way for exploit whereby you inject an input value that returns something matching the initialized database value, such as an empty string or null in JSON, and this is compared as part of the security control. Frameworks often let you pass in arrays and other non-string data structures using non-standard syntaxes. For example, in PHP, Ruby on Rails lets you do something similar by providing a query or post parameter with a key but no value. In other words, param key results in the following server-side object. In the example above, this means that during the race window, you could potentially make an authenticated API request as follows. It's possible to cause similar partial construction collisions with a password rather than an API key. However, as passwords are hashed, this means you need to inject a value that makes the hash digest match the initialized value. Time-sensitive attack. Sometimes you may not find race conditions, but the techniques for delivering requests with precise timing can reveal the presence of other vulnerabilities. One such example is when high-resolution timestamps are used instead of cryptographically secure random strings to generate security tokens. Consider a password reset token that is randomized using a timestamp. In this case, it might be possible to trigger two password resets in two different users, which both use the same token. All you need to do is time the request so that they generate the same timestamp. This lab contains a password reset mechanism. Although it doesn't contain race condition, you can exploit the mechanism's broken cryptography by sending carefully timed requests. To solve the lab, identify and generate password reset token. Obtain a valid password reset token for user Carlos. Okay, let's try solving this one. This sounds more promising than the one from before. It's so annoying. I really hate this lab. So did we get the winner Peter account? Yeah. Winner Peter. So there's a password change. Wait, what? What is the challenge about? Wait, it's on this? Okay, let's try sending the email. Okay. What happens? So that's not the... Wait, what? Wait, where is the... Where's the reset password feature? Is it here? Oh, okay, my bad, actually, my bad. So let's try submitting the reset. So let's try testing it. So let's send it to repeater. Can I actually like change this? And did I get 2 emails? Nope. But what if, wait, did I get it? Okay, no. But we can still check. We can just create a repeater. No, we can create a group that we can send in a same time frame. Wait, parallel. Let's add one more. What about that? Okay, so it's still all different. Wait. Hmm. What if we put it parallel again? What happens? Okay, so I don't understand how this works, so let's just hit the solution. Yeah, different token. Yes, it's consistent. Yeah, this is where I'm at now. Wait, what? I didn't notice that. For real? Oh yeah. Wait, I didn't thought about that. So let's just send it. So this is the second session token, probably. Yeah, right? Yeah, it's different tokens. So what about now? Hmm. Oh yeah, it has the username. Wait, for real without the server? Interesting. So Carlos doesn't need the email, so oh, because the email takes the username and the email, yeah? Maybe. Okay, so we actually can solve this one. So I didn't think about the PHP. Yeah, I forgot about that. And I should have remembered because I just read that. Yeah, but this is very interesting. Yeah, I saw the response. They always have like extra 1 second. So that means it's checking it in a sequence. But in PHP, using different session tokens, PHP session IDs, you could make the time faster. So yeah, that's a bit cool. Let's continue. Okay, how to prevent trace condition vulnerabilities. When a single request can transition an application through invisible substates, understanding and predicting its behavior is extremely difficult. This makes defense impractical. To secure an application properly, we recommend eliminating substates from all sensitive endpoints by applying the following strategies. Avoid mixing data from different storage places. Ensure sensitive endpoints make state changes atomic by using the data store's concurrent features. For example, use a single database transaction to check the payment matches the current value to confirm the order. As a defense in depth measure, take advantage of data storage integrity and consistency features like column uniqueness and constraints. Don't attempt to use one data storage layer to secure another. No. Okay, don't attempt to use one data storage layer to secure another. For example, sessions aren't suitable for preventing limit overrun attacks on databases. Ensure your talk session handling framework keeps sessions internally consistent. Updating session variables individually instead of in a batch might be tempting optimization, but it's extremely dangerous. This goes for ORMs too. By hiding away concepts like transactions, they are taking full responsibility for them. In some architectures, it may be appropriate to avoid server-side state entirely. Instead, you could use encryption to push the state client-side. For example, using JWTs. Note that this has its own risk, as we have covered extensively in our topic on JWT attacks. Interesting. Let's copy this to the notes. Okay, so we finished the path. So yeah, this path is actually very annoying and very hard because the second lab, yeah, I forgot which lab, needed the Burpsuit Pro, and using not using Burpsuit Pro makes it very hard to solve, so it's very annoying. And yeah, the second one is the one that was unsolvable. I don't know why. I literally did what the solution did. I don't know what I did wrong. If you guys know, you can explain. But I felt like I did it right, so I don't understand what went wrong. So yeah, it's very annoying. But let's continue moving on. Yeah, it's day 7. We cleared 7 paths already. Clickjacking, server side, have traversal, race condition, API, file upload, server side. Yeah, and that's it for today. Thank you.